Okay, folks, let's talk a little bit more about equilibrium. Gave you some examples in the last video, and now we just want to kind of get a better understanding of what it looks like when a system is actually at equilibrium. So what we need to do is go back through and we have to bring that stuff about rates that we talked about earlier in the course and use that again. And now instead of having one rate, we're going to have two rates. So we're going to have kind of the rate of the reaction that we've already been talking about, which would be the one going in the forward direction. And we've learned all the theory and things around what controls how fast that rate goes. And then we're going to have the rate, though, because this is happening in a closed system and it's at equilibrium, we have a second rate, which describes how fast the reverse reaction is going. So we have the forward reaction and the reverse reaction. So to get to equilibrium, we have to get these two rates to be equal to each other. And there's doesn't necessarily mean that there has to be equal amounts of everything that's in the reaction, just equal rates of A and B turning into products and the products turning back into reactants. So there are lots of factors that affect what that balance is, and we're going to look at how to calculate some of those in the future discussions. But for now, this is the point at which equilibrium has happened, is when these two rates are equal. And we'll take a look at what that looks like in a graph in just a second. Okay? Just to make sure we have a couple of words figured out, macroscopic. So that means if I was to look at let's say I had a beaker or a flask, and a beaker can be a closed system. If you have a beaker and it just has water in it, and we ignore a fact that there's a little bit of water evaporating, whatever's going on in this system inside the beaker is considered a closed system. We don't actually have to cover it. We can just ignore the little bit of water that goes in and out. And so aqueous solutions, a lot of the stuff might occur in closed systems, or we might have a gas. And in the case of a gas, we'd have to actually put it in a closed system. So we might put it in a bottle and then put a stopper on it. And then whatever the gas is inside, it's trapped and nothing can be added, nothing can be removed. So in the case of a closed system, when we look at it and we don't see any changes in color, any changes in pressure, any changes in pH, nothing that we can see with our eyes is changing, we say that that system is macroscopically stable. And that's how we know something's at equilibrium. One of the clues is we can look at it and see there are no changes happening. Okay? But even though there's nothing that seems to be happening at the macroscopic level, we need to remember microscopically, this is still happening. The reactions are still proceeding. They've just gotten to a point where they're equal to each other, and from observable things with our eyes, we don't see anything changing. Okay, so if we take a look at a graph of what this looks like, typically I graph there's different ways of doing this, but I like to graph concentration on the y-axis and time on the x-axis. And then we have forward and reverse reactions going on here. So the forward reaction, I'm going to be measuring the change in concentration of the reactant. So I would just pick one if there were two. Typically, one of them is easier to measure. So the forward reaction, the line on here is representing how the concentration of the reactions changed over time. And if we run a reaction, it kind of makes sense that we would start out with a high concentration of reactants here. So the reactants here are fairly high concentration. And then that concentration lowers as the time of the reaction goes on because the reaction is proceeding. So let's just use that same reaction. A plus B forms AB. Okay? So A and B are being used up, and we would see the concentration of those reactants drop over time. And the reverse reaction, what we're measuring there is the change in the concentration of the products. And so we see the opposite trend with the products. We start out with none of them, at least in this case, we have no products. And over time, the product concentration increases. And then in this reaction, we come to an equilibrium at which both of the concentrations are the same. So we have the same amount of products and reactants at equilibrium. That's not always the case. It is the case in this one, and we'll look at some examples in a minute where you don't necessarily have to have equal amounts of products and reactants at equilibrium. What you do have to have, and what we do know then, is that the rate of the forward reaction and the rate of the reverse reaction at equilibrium are equal. It doesn't necessarily mean that they're equal concentrations, but in this example we've drawn up, they are. So at this point here, this dotted line shows you when equilibrium was established in our system. Okay? And you can kind of see if this makes sense. As you use up reactants, the concentration of the reactants goes down. And so as time proceeds and the concentration of reactants goes down, the rate forward will actually begin to slow. So even though it was fast at the beginning and things were moving from here, let's just say it was fast at the beginning, right? The initially was very fast. It begins to slow as the reactants are used up, and we know that from our discussion of rate law, that as you use up reactants, the reaction goes slower and slower. But the opposite is true of the reverse reaction. There are no reactants here, products here, so it begins very slowly as products are being made, but as more and more products are made, this rate is speeding up. So while the rate of the forward reaction is slowing down, the rate of the reverse reaction begins to speed up because we're increasing the amount of AB that's present in our system. And eventually we get to a point where this is slowed down enough and this is sped up enough that they equal each other. And at this point in this reaction, that's a 50-50 balance. Not always so, but in this reaction it is. So we can explain equilibrium by using rates. We slow or speed up reaction rates depending on which way this reaction is moving. At the beginning, it's moving from left to right. And then at the very beginning, the reverse reaction is fairly slow. But as we move through time and we get to equilibrium, this reaction and this reaction become equal to each other. Okay. So at the beginning reaction, the rate of the forward reaction is fast, the rate of the reaction is slow. And we're assuming, you don't have to, but we're assuming then that you begin with no products. Okay? And that would give me a very fast forward rate. So the rate forward is fast as compared to the rate reverse, which would be very slow. Okay? So rate forward is greater than rate reverse. As time goes on, the products increase and the rate of the reverse reaction will increase. So as time goes on, we start to use up some of the reactants. That brings this rate down. We start to make some more products. So that brings this rate up. And then they become, so this one will slow and this one will speed up. Okay. And then eventually we get to a point which we call equilibrium, where those two rates have come to be equal to each other. So that's when we see macroscopically nothing is changing. The color, the pH, whatever we were measuring stays the same. And it seems to be static, though underneath we know that these two reactions are continuing to happen just at exactly the same rates. Okay? So that's how we know that equilibrium has been established. Now you can look at a reaction rate like this one, and you'll notice the same thing. We started with no products, only reactants. So at this beginning phase right here, we could say that the rate of the forward reaction is greater than the rate of the reverse reaction. Right? And so we see reactants being used up, and we see products being formed. And equilibrium is achieved here at this point where both of the concentrations appear to stop changing. Equilibrium, which they do, they stop to changing, but underneath we know it's very dynamic and things are still moving back and forth. But this time, the reaction rates have balanced out at a point where the products and the reactants are not of equal concentration. So we actually have more product being made than we have reactants being made. So what causes this to be not an equal concentration as we saw in the other ones? Well, if we go back and we take a look at some of our graphs that we drew for our reaction rates, we know that when we do some reactions, we start out with reactants, and we turn those reactants with some activation energy, and we turn them into products. And we know that the activation energy was labeled as the energy it takes to go from here to here. That's the amount of energy we need to get reactants turned into products. Well, that's just the activation energies, or the energy for activation of the forward reaction. The activation energy for the reverse reaction is actually right here. So we got the activation energy of the forward reaction, and then we'll call that EA1. And we have the ones for the reverse reaction, we'll call that EA2. It actually takes a lot more energy to make the reverse reaction happen. You need to have this whole increase in activation energy to get the reverse reaction happening. So that makes the forward rate, the rate of the forward reaction, it makes it greater than the rate of the reverse reaction. So as we slowly use up the reactants, this rate starts to get slower, and this rate starts to speed up. But to get an equivalent speeding up of this rate, we have to have a lot more reactants on this side. So we have to have a lot more products, on this side. And we have to increase this concentration a lot more because it's much harder to get an effective collision going in the reverse direction. So in the end, we end up making a lot more products. We have a lot less reactants. And that difference is because of this EA difference. In the forward reaction has a lower EA than the reverse reaction. Okay? So it takes more, a bigger change in concentration of products in order to be able to match. Because again, here we get to the point where rate forward equals rate reverse. And so to speed the reverse reaction up enough, given that it has this relatively huge activation energy, we need to increase this concentration way more and bring this one way down so that the two of them will balance out. Okay. So before we look at another example, what would the graph look like if we were going to have lots of reactants left at equilibrium, but very few products made? So take a minute, just pause your video and take a look at this graph. If you needed to repeat this graph here, what would it look like so that the reactants made, there were lots of reactants left, but very few products made? What would that reaction look like? So pause your video for a minute, see if you can sketch a little graph to show what that looks like, and then we'll take a look at the answer. Okay, so the answer would look something like this. We would have a graph, concentration on the side, time along the bottom. And if we were to take a look at what's going on here, our reactants then would start up here, but they would also finish fairly high. That's what I'm suggesting, that we still have lots of reactants left at equilibrium. And our products would start again at 0 in this example. We would use some of them up, but then they would finish fairly low. And so at this point where we hit equilibrium again, why did that finish the way that it did? Well, if you take a look at your reaction rate graph, you need to have a reaction in which, to make them equal, there would be lots of reactants and very few products. So that means that if there's lots of reactants left, we need to have lots of them because that rate must be slow. And the best way to illustrate a slow reaction rate would be to give the forward reaction a very high EA. So we would come up something like that, saying that that's the EA of the forward reaction. And to get an EA that's smaller for the reverse reaction so that it happens easily, we'd have to end our products there. So there's the reactants, and there's the products. And if we take a look at the two EA values, so you can see now that this EA is smaller. So it's easier to get this reaction happening. So we can get a good rate going with a lower concentration. This is the EA for the forward reaction, and it's much harder to do. So we can see that we'd have to keep the concentration high to be able to keep this rate equal to the product rate. Because remember, again, even though these two are not equal, the rate of the forward is equal to the rate of the reverse. Okay, so and this would be an endothermic reaction, and it's resulting in lots of reactants left and very few products left. Right? So this is one of the things that a chemist is, if you're working as a chemist in industry, this is one of the things you're doing, is looking at a reaction like this that might be commercially important and trying to find a way to shift this equilibrium, because we don't want, at the end of our run of the reaction, we don't want most of the reactants left. We want everything turned into products. So you'd be looking for catalysts, you'd be looking for conditions which would change these rates of reactions so that when they were done, we'd actually end up using up the reactants and making lots of products. Right now, this way this reaction looks, it's not a very viable reaction for commercial purposes because you're not really making very much of what you're trying to make. Okay? So you might have read a video about the Haber process and how to make ammonia and nitrogen compound for fertilizing, and what went into looking at that rate if you've looked at some of the material that I posted. Okay? That's an example of where chemists have worked to fiddle with these rates to create conditions so that we maximize the amount of products that we make. Okay, let's just take a look at one more graph and then we'll wrap this video up. So we take a look at this reaction. We can take CO2, and if we heat it enough, it will thermally decompose into carbon monoxide and oxygen gas. Let's just take a look at these three conditions here. If we were to begin the reaction by only having CO2 in the flask, and we will get to conditions where you have everything present, not just CO2, not just the reactants, but the reactants and the product can be there at the beginning. What we would have is if we had an amount of CO2 here, as the reaction started, that amount of CO2 would slowly come down. And then if this was a closed system, which we are assuming it is, it would balance out. Okay? The reactants, on the other hand, would have been down here at 0. And as the reactants were used up, we would end up making some products. And possibly it comes out to here. I'm just guessing and making some relative graphs of what everything looks like. Okay? So that's exactly what we've been talking about. Now, one of the other characteristics of an equilibrium is that you can actually, we can stress the equilibrium out. And an equilibrium will respond to that stress and reestablish its balance point. So right here we see in this equilibrium, that's when the rates of the two reactions became equal to each other. And we see that there was no change in the concentrations of the reactants or the products. But if we add a stress to the system, so a stress can be many different things. We'll talk about a bit more of this next week. A stress in this case could be we add some CO2 to the system. So that would mean that this concentration of CO2, well, that's the worst straight line ever. The CO2 concentration would go up. And if that was true, that the concentration of CO2 went up, then we would see the rate of the forward reaction increase. Because as they get more concentration, reaction rates go faster. And so it would now be greater than the rate of the reverse reaction. But it hasn't changed. We haven't touched the concentration of products at all. So the rate of the reverse reaction remains unchanged. This one gets faster. And so what would that do to our concentrations? Well, it would mean that we would start to use up reactants again. And so it would start to use up reactants until it leveled out. And if we're using up reactants, then we're making more products. And so the products would start to be made until it leveled out. And again, we hit a point where we have a second equilibrium. We have a new equilibrium established at the point where those two things balance out. Okay? And that's because to slow this rate down, we had to use up reactants. To speed this rate up, we had to make products. And eventually, again, we get to the point where the rate of the forward reaction and the rate of the reverse reaction equal one another. Okay? So that's one of the characteristics of an equilibrium system. When you stress it, it can respond and reestablish equilibrium. Okay? Now we look at one other stress, we can also take things away. So this is our second stress right here. If we were to remove CO2 from the system, then that means that this would drop. If that drops, that means the rate of the forward reaction would then go down. And so it's now less than the rate of the reverse reaction. Okay. So how do we respond to that stress? How do we fix that so that everything comes back to equilibrium again? Well, if we want to speed up the rate of the forward reaction, then what we need to do is get some more reactants. We need to have those reactants reappear. And since the rate of the reverse reaction is faster than the rate of the forward reaction, that's exactly what's going to happen. This is going to start to turn and make more reactants because the reverse reaction is faster until it gets to a point where that levels out. What effect did that have on the reverse reaction? Well, that means that some of this got used up. So this starts to get used up, and then it levels out, reestablishing equilibrium once again. Okay, so at each one of these dotted lines, the rate forward equals the rate reverse. And you should be able to take a look at each of these starting points. So here, here, and here, and explain why one of the rates is faster, and then explain what it would take to bring those rates back into equilibrium, back so that the rates are equal to each other again. Okay? So in this work, remember, if it's we want to slow a rate down, we have to use up some of the concentration. So we used up reactants here. The concentration came down until it got to equal. We make products while we're using up reactants, so the rate goes faster and comes to here when it's equal. So that kind of thinking, bringing that rate law, the rate collision theory material forward, helps us explain why an equilibrium can be established. Okay. Now we'll give you some time to work on this. There's a gizmo on the Explore Learning website called Equilibrium and Concentration. I posted a modified worksheet on the classroom for you to use, as well as I posted some instructions of how to log into the Explore Learning site. So please check that out. And this will give you a chance to work with some more equations, to look at some data and look at graphs and get a little practice at interpreting what's going on with these graphs as equilibrium is stressed and then as equilibrium is established. Okay, so we'll leave you with that and we will talk more next week. Thanks.